Hi and welcome to Parabolas Day 2. So we're going to kind of jump around a little bit in here for today, but we're going to start with the definition of a parabola is the name of the lesson. Suppose you're viewing a cross-section of a mirror. Where would the incoming light be reflected in each type of design? Sketch your ideas below. So in mirror number 1, the light is coming directly into the mirror. So it's going to hit the mirror, and then it's going to bounce backwards, and it's going to go directly back in the direction it came from. So it's going to come down, hit it, and then bounce back. Come down, hit it, and then bounce back. For mirror number 2, they meet, it looks like, at a pretty sharp angle, probably a 90-degree angle. What's going to happen is when the light comes down, it's going to reflect and then go off in a 90-degree angle. So every time you bounce a light, it's going to bounce back and around. And then if you have a curved mirror, what's going to happen is it's going to come down like this, and then it's going to bounce back. Come down like this, and bounce back. Come down like this, bounce back. Come down like this, and then bounce back, something like that. So they're going to kind of be all over the place. So we're going to actually save the discussion for the telescope design in class. We are going to look at the definition of a parabola. A parabola with a directrix L and a focus point F is the set of all points in the plane that are equidistant from point F and line L. So figure 2 to the right illustrates this definition of a parabola. In this diagram, FP1 is equal to P1, Q1, so they're congruent. And FP2 is congruent to P2, Q2. And FP3 is congruent to P2 or P3, Q3. So showing that for any point on P, the parabola, the distance between P and F is equal to the distance between P and line L. All parabolas have the reflective property illustrated in figure 3. Rays parallel to the x-axis reflect off the parabola and through the focus point F. Thus, a mirror shaped like a rotated parabola would satisfy Newton's requirement for his telescope design. And that goes back into the discussion that we'll have in class. I want you to think about something that is shaped like a parabola that's used in technology, I guess would be the right word for it. So I want you to think of a real life example of a parabola used in technology today. All right, so we will continue with this discussion in class and jump into the actual math. So finding an analytic equation for a parabola. Given a focus and a directrix, create an equation for a parabola. So my focus is the point 0, 2, my directrix is the x-axis, and the parabola is the set of all points xy such that xy is equidistant from F and the x-axis. So that would mean that this has to be congruent to that. Let any point xy on the parabola P, let A be any point, xy on the parabola P. Let F prime be a point on the directrix with the same x coordinate as point A. What is the length of AF prime? So this distance from here to here is actually the distance of y. So that means that AF prime is equal to y. Use the distance formula to create an expression that represents the length AF. Okay, the distance formula, in case you have forgotten, is d equals the square root of x2 minus x1, the quantity squared, plus y2 minus y1, the quantity squared. We learned that last year in geometry. So we're going to create an equation that relates the two lengths and solves for y. So as I go back, I'm going to look at my parabola here. I'm going to draw a right triangle, like so. This distance from here to here has to be x. And this distance inside here, if the whole thing is y, and we know that this is at 2, this must be y minus 2. So if you remember using the distance formula last year, this is what you did. If you didn't use the distance formula, you used a squared plus b squared equals c squared, which might be actually easier to see with this drawing. We are looking for the distance AF, and if I use the Pythagorean theorem, it's actually a little bit easier to see it. So, and I want to solve for c squared. So c squared equals, solve for c equals a squared plus b squared. So c squared is equal to, pick a to be the x distance, so x squared, plus b, the y distance, is y minus 2, so y minus 2 squared. And then just take the square root of both sides. So c equals the square root of x squared plus y minus 2 squared. And we're going to replace c with AF. Well, AF has to be equal to AF prime, and AF prime is equal to y, so I can take the two equations and set them equal to each other. So y is equal to the square root of x squared plus y minus 2, the quantity squared. Now I need to clean this equation up. To get rid of the radical, I need to square both sides. So y squared equals, square root cancels each other out, x squared plus y minus 2 squared, which means I need to write it twice. And actually multiply it out. So y squared equals x squared plus y squared minus 4y plus 4. And I want to get all the x's on one side, all the y's on the other. And when I go to subtract y squared from both sides, they cancel each other out. So 0 equals x squared minus 4y plus 4. So subtract the 4y. So you have negative, or sorry, add the 4y, my bad. So plus 4y equals x squared plus 4. To get y alone, divide everything by 4. So I will have y equals 1/4 x squared plus 1. So this is the equation that I have found using my focus and my directrix to find for my parabola. And we need to verify that this equation appears to match the graph shown. So if we go back up and look at the graph, I need to have an actual point on the graph. I know that the distance between here and here have to be the same because any line drawn from the focus to the parabola and then to the directrix have to be congruent to each other. So if I know that my total distance here is 2, this point here has to be halfway. So that means that this point has to be the point 0, 1, and that point has to be on my graph. So I'll kind of recreate that down here. This was my directrix. This was the point 0, 0. I know that the focus is the point 0, 2. So that means that this has to be congruent to this. So this point over here is the point 0, 1. And it must be halfway. So if I know that the point 0, 1 is on my graph, then when I substitute into the equation, it better check. So I'm going to put 1 in for y, 0 in for x. So 1 equals 1/4 0 squared plus 1. Well, 0 squared is 0, so 1 equals 1/4 times 0 plus 1. When I multiply everything times 0, I get 0, so 1 equals 1, and it works. Therefore, that equation is a valid equation for my parabola. All right. Demonstrate your understanding of the definition of a parabola by drawing several pairs of congruent segments given the parabola, its focus, and directrix. Make or measure the segments that you drew to confirm the accuracy of your sketches in either centimeters or inches. So we will work on this one, and well, actually I want you to work on this one with a ruler and measure them. I'll kind of get you started. That would be one line. It's kind of hard for me to draw on here. I'd have to measure those and make sure that they were the same distance. And I want you to do at least 7 lines. Number 2, derive the analytic equation of a parabola given the focus of 0, 4 and the directrix y equals 2. Use the diagram to help you work this problem. So label a point xy anywhere on the parabola. It can be anywhere. It doesn't have to be right on a line, but it makes it a little bit easier. So that's my point xy. Write an expression for the distance from the point xy to the directrix. Well, if this is my directrix right here, and my entire distance is measured in y, and this is 2 units from here to here, that means that this is y minus 2, because we're pretending we don't know those points. So the expression from the distance from the point xy to the directrix is just y minus 2. Write an expression for the distance from the point xy to the focus. Well, that goes back to trying to draw a right triangle here, but it's not going to work because of my picture, so we're going to have to use our distance formula. And my distance formula from this point to the point xy would be x minus 0, the quantity squared, plus y minus 4, the quantity squared. And b is what AC or what C has to be equal to. So we're going to say apply the definition of parabola to create an equation in terms of x and y. Solve this equation for y. So y minus 2 equals the square root of x minus 0 squared plus y minus 4, the quantity squared. So I'm going to have to square both sides. square both sides. So over here, I will have a write it twice. And here in the square and square root cancels each other out, so I have x squared plus another write it twice, y minus 4 the quantity squared, so I might as well just write it out now. Now I have to multiply, so I will have y squared minus 4y plus 4 equals x squared plus y squared minus 8y plus 16. Now I need to get this equal to, get y's on one side, x's on the other. Here my y squareds cancel each other out. And I'm going to add 8y to both sides. And then subtract 4. So when I do that, I end up with 4y equals x squared. That will cancel. That one cancels. Plus 12. So then I'm going to divide everything by 4 to get y alone. So y equals 1/4 x squared plus 3. Now, part E asks, what is the translation that takes the graph of this parabola to the graph of the equation derived in example 1? My equation for example 1 was y equals 1/4 x squared plus 1. So the only thing that's changing is that plus 1 and plus 3. And if that's the only thing that's happening, this is a translation down 2 units. So translation down to, this is TWO, 2 units will take this graph of this parabola to the one derived in example 1. So if I simply take that graph and move it down 2 units, I end up in the same place, or end up in the same place. All right, that is it for today.